Now, when we have a look at thermal resistance network, we said the rate of heat convection into the wall, and rate of heat convection into the wall is equal to H1 A T alpha 1 T infinity 1 minus T1. T infinity 1 is that temperature, and T1 is the temperature of the inside of the wall. Now that should be equal to the rate of heat conduction through the wall, which is equal to that one, Ka. K is a constant, A is the area, T1 minus T2, where T1 is that temperature here, and T2 is the temperature of outside of the wall. Then we got rate of heat convection from the wall. So this is heat convection from the wall, which is equal to H2 A T2 minus T infinity 2, which is that temperature here, the outside of the wall, and the temperature of the surrounding. Okay. Now, if we rearrange that one, and bring the H1 over A all the way down, so I divide everything by 1 over H1A. Yeah, here I divide everything by L over Ka. Here I divide everything by 1 over H2A. Now, L over Ka is the resistance of the wall, and 1 over H1A1 is the convection, and that's also the convection. So you need to remember this one. R for the convection is equal to 1 over H1A, and R for the wall, the solid one, is L over Ka, where L is length, A is area, K is constant. Let's go to next one. Now, if I add all the numerators and the denominators together, let's say I say, oh, the R convection plus the R wall and R they are the total R. So I can call that one the total R, and on the top I can call T1 minus the T2. T1 infinity, T infinity 1 minus T infinity 2, which is the difference between this one, and that one. Okay. Now, if I look for the R total, the formula for the R total is R convection 1 plus R wall plus R convection 2. And I can add that one. The units are going to be in centigrade per watts. Now, the heat transfer area is constant for a plane of wall because the wall is not changing in dimension. The rate of heat transferred through the wall separating two medium is should be equal to the change in the temperature. And it should depend on the thermal resistivity and thermal conductivity between the medium. Okay, now if we summarize that one and say the rate of heat transfer between two surfaces is equal to the temperature difference divided by the thermal resistance between the two surfaces, and this is how we calculate the heat resistance. So we got delta T, before we got delta T, we got Q equals to delta T over R. Rate of transfer is equal to the ratio between the temperature and the resistivity. The higher the ratio is, the bigger the value of the heat transfer. The lower the ratio is, the less the value of the heat transfer. For a very good insulation, you have a very high R value. If your home system is perfectly insulated, the R will be a high value, high resistance. No matter whatever the temperature is, the heat is not going to go out, so you can have like a warm environment inside. If the value of the R is very small, then in this case the heat flow rate will be a lot. So properly insulated house, Q is going to be low. Not properly insulated house, Q is going to be very high. The unit for that one is centigrade. For the Q, the unit of that one, joules per second, watts. If it's temperature, the unit for that one is is centigrade. For the R, the unit is centigrade, the temperature over watts power. Okay, next one. Okay, now if we have a look at the temperature drop across any layer, it's equal to the heat transfer at that specific time, which will be given by the gradient, which will be given by this gradient. So not fast heat transfer rate, fast heat transfer rate, fast heat transfer rate, bit more fast, now less heat transfer rate. The steeper the gradient is, the faster the heat transfer rate is. According to the Newton law, we got Q equals to UA delta T. Now where U is the overall heat transfer coefficient. Now if I replace that one, UA equals to 1 over R total. So I got that value. U is the heat transfer coefficient and A is the area. That will give you 1 over R total. If the area is a unit area, which means the area is 1, U will be equal to 1 over R total. Okay, let's go to the next one. Okay, so in that case, if I got the total heat transfer, the surface temperature, I can find the surface temperature by using this formula. If in this case, I'm given the value of the Q, I am given the value for the R, I am given the value of that one, I can find that missing bit. If one of these variables is missing, I can simply find that one. Okay. What if we got a multiplayer plane walls? Now imagine we got a wall that consists of 7 layers of different materials. The thermal resistivity of every material is different. Conduction is different. So we need to find out, we need to separate the wall into multiple layers, and we need to find the L over Ka for each wall. L is the thickness of the wall, A is the area. Maybe the area remain the constant, the thickness might be different, and the K value will be different. And we will add all the values of the R's to find the total R. Now we got this formula already. Now we know the R total is equal to R convection 1, R of the wall 1, R of the wall 2. Imagine there are 2 solid walls inside, different materials, and R of the convection 2. So R of convection 1 is 1 over H1A. R of the wall is L over Ka. Now the second wall is L over Ka, but L is different and K is different, so L2 K2. And for the other one, 1 over H2A, where L is the thickness, H and the K's, they are the constant, and A is the area of the wall. So imagine this is, so here in this side convection is happening. So this is the resistance because of convection. This is material 1. Conduction is happening. This is the formula. This is another material with a different thickness, not drawn to scale. This is the formula for the resistance of that one. And here again the convection is happening. So we got another formula for that. We have to add all these to get the total R total. So we need to find out the R total. To find the R total, we need to add all these values. Okay.
What happens if you've got like a cavity?
Okay. So we have the values. Now if I want to find out the T1 here, and I have given this value, and I have the convection rate, I can rearrange the equation like that, which is Q equals to T infinity 1 minus T1 divided by the R convection, and I can rearrange that to find the value of the T1. If I want to find the T2 here, I can use that formula again. I can do T infinity 1 minus T2 divided by the convection 1 plus R of the wall 1. So I need to add convection plus I need to add that one because the temperature gradient is from 1 all the way to 2. If I want to find the T3, I'm just going to look from that side. I will say like, oh, T infinity 3, which is high temperature, minus that temperature, divide by the convection that is happening on this side, R of a convection, and that's how I can find the T1, T2, and T3. So this formula is quite important. Now, if I want from T1 to T2, if I want to find T1 to T2, this formula here, I know T1, T infinity 1, which is here, minus the T2, which is here, is divided by the R convection 1 and R convection of the wall. And R values are given by, where did I wrote the R values? That one. So I need to copy these values back into the formula. Now this is only if they gave me the H values and they gave me the dimension of the wall and they gave me the K value. If they give R value straight away, we can use that one. Okay, we want to find the heat loss through a wall. There is a wall 3 meter high, 5 meter wide. We can find the area 3 times 5, and the thickness is 0.3 meters. We need to make sure everything is in SI units. The value for the K, which is the thermal conductivity of the wall, is 0.9 watts per meter Kelvin. And on a certain day, the inner temperature and the outer temperature were measured. The reading was 16 and 16 degrees centigrade and 2 degrees centigrade. We need to find the rate of the heat loss through the wall. So we got the area 3 times 5, K is 0.9 watts meter Kelvin, T1 is 16, T2 is 2 degree. Okay, and we are given the thickness as well. So first thing is we need to make few assumptions. Our most important assumption is a steady flow of the heat, which means the temperature at each part of the wall as it's far from the T1 is constant. So temperature remain the constant. Okay, the heat transfer in one dimension. So we assume the heat transfer in one dimension, and there will be a temperature gradient exist, because if the temperature is same, the heat transfer will not take place. We got the thermal conductivity. First thing, we find the area. We use the formula. Let me just write it down here. We got the formula Q equals to K A T2 minus T1, T1 minus T2. Okay, let's do that way. It doesn't matter, to be honest. Okay, T1 is going to be high temperature. The value of the K is 0.9. So you put 0.9. The value for the A, which is 5 times 3, is 15. And the T1 minus T2, T1 is 16. 16 minus 3. It's good to convert that into Kelvin, but you will get the same difference. Now, do not forget this is divided by the L. So divided by the 3. If you put that in your calculator, if you put that in your calculator, you will get the Q dot. Q dot, which is going to be 630 joules, because this is a heat transfer. But because there is a dot, it's joules per second, which is equal to watts. And this is how we find the heat transfer rate. These are the formula. You find the value for the R, use that equation. Q equals to change in wall divided by the R of the wall. R of the wall is actually L over Ka. Find the L over Ka, put in this equation, you will get exactly same answer. Thickness is actually 0.3 meter. Yeah, L is actually thickness of the wall. So which is that bit, 0.3 meters. Yeah. So I put 3 meters, 0.3, and that will give you 630 as an answer.